last we met, I had talked mainly about physics as a description of the universe, and in that process had defined the notion of displacement, because in a coordinate system that I could create, I can identify the locations of objects or events in a coordinate system, and then by definition I say that the final position minus the initial position is called the displacement. So I have a way in my universe of describing the changes in positions. Indeed, it's true that if I wait for a long period of time, the positions of objects in my universe can change quite a bit. You'll find things to be far removed from where they were initially. And indeed, during that time interval, when I'm not making a measurement of position, it's a scientific fact, a realization, that I don't know what was happening in between. I do not know. I can imagine what happened, and that imagining is known as the trajectory of an object, as I imagine that it goes through a continuum of positions from one location in the universe to the other. I really don't know. And a way that I can get around that is to look at the universe very frequently, in which case I say, don't let the positions change that much. Look very, very, very frequently. That is, let the time interval of your measurements be quite small. And if you make the time intervals go quite small, then in fact objects can't change their positions very much. And so you get small changes in position. And so a thing that I'm leading you through now is that I'll replace this idea delta x, a large change in position, with a change in position dx, which is quite small. I even imagined, in fact, that change in position could be infinitesimally small, because it's arbitrary. And although I don't know exactly what infinitesimally small means, I understand that I can just arbitrarily decrease the size of the interval. And so those two things are exactly the same thing, the displacement. It's just an argument about scale. And then once I've defined displacement, I defined for myself the velocity, and I talked about velocity being a vector, but I didn't give that any sort of flesh in the last discussion. And so today I'm going to say quite a bit more about the nature of velocity as a vector, but more importantly, by definition. The velocity is the displacement, delta x, divided by the time, delta t, in which that displacement takes place. But of course I've got this mysterious thing where positions change and I don't know what happens in between, and so this is only defined on average. What happens during the entire interval is rather a mystery. I'm only describing in general terms the rate at which the displacement happens. But of course I have this new piece of, or this new concept in my artillery where I can make the time interval small and call it dt. A very small interval of time is a very small displacement. And when I do that, relying on small intervals of time, I get a closer and closer and closer average velocity over the entire interval, because the interval becomes so small that the velocity can't possibly change much on the interval, and it becomes the velocity. The thing that I was thinking about with that is that I have in my car a speedometer, and technically, because the velocity has direction associated with it, my car really does have a velocimeter, because I can look at the dashboard and it tells me I'm heading north, south, east, west, which is a direction. But more importantly, my dashboard tells me the speed I'm going at any instant in time. At any instant in time, it tells me, right now, you're going 35 miles an hour. But not really. It's telling me on average. How does it know? How does a car know what your speed is at any instant in time if theoretically, physics-wise here, I can't even define that without doing an instantaneous thing? Well, it's the rotation of the tire that determines what's read on the speedometer. And the tire rotates in such a short time interval that the speed can't change much in one tire rotation, particularly when you're going down the highway. Your tire rotates about in a tenth of a second. In a tenth of a second, speed of the car can't change much. And so the average speed that's reported on the dashboard as if it's instantaneous is certainly accurate enough. And so that's the velocity, which is the quantity that describes the rate at which displacements happen. And I also talked about the acceleration, which is the change in velocity over time. And I realized that, of course, velocities don't necessarily remain the same as I make observations of the universe, and the velocity can change. And by just absolutely identical arguments, I can say that the acceleration is the change in velocity with respect to time, or dv divided by dt, and I can define an instantaneous acceleration. And of course, this process can go on infinitely. I can keep defining new things on and on and on, but we'll stop here because it turns out that we've discovered over centuries of doing physics that this is sufficient to give me a good description of motion in the universe. So an advantage that I have here, looking at these definitions, is to realize that they can be interpreted when I make motion graphs. For example, it's a simple thing for me to make a graph of the velocity of an object as a function of time. So here I have a graph where on the vertical axis I place the velocity, and on the horizontal axis I place the time. And so I make some observations of velocity. In order to measure a velocity, I have to make two measurements of position. When it comes to uncertainty in measurement, that causes me some trouble. I have to be really careful here, because the more measurements I make and the more calculations I do with measurements, the more my experimental error tends to balloon. But I make two measurements of position, that gets me a velocity, and I make two more measurements of position, that gets me a velocity, two more measurements of position, that gets me a velocity. And so I can make a graph of data. Well, here I'm going to do this godlike thing that I do with graphs. I'm going to sort of pretend that I know in advance what the graph should look like, or what the trajectory actually looks like. And I'm just going to imagine that perhaps I start out here with some initial velocity that I'll call v0, and I'll imagine that it goes like this. A very simple graph, certainly not the most general graph that I can draw, because it's a straight line, and the mathematics of straight lines is something very easy for us to manage. So I have a graph that tells me that my velocity starts at 0, and then later on in time it ends up here. Maybe I just made two measurements of velocity, or perhaps I made more. It's not really an experimental graph, more of a theoretical graph. And so I look at this graph and realize that in a certain time interval, from here t is equal to 0, the initial time down here, the axis, to the final time here, and so my time interval delta t is defined by t minus 0, which of course is just t. It's a very convenient way of writing that. That in that time, my velocity increased. So I'll sort of draw in here and make a triangle for myself. My velocity increased from here to here by an amount delta v in a time interval delta t. It's a familiar graph. It's very similar to one that I drew in the last lecture. Well, look what happens here if I look at my definition of acceleration. I find that delta v divided by delta t is in fact the rise of the graph divided by the run of the graph, which I've come to recognize through all my math training as the slope of the graph. Well, this, of course, is by definition the acceleration. So what I learned from this is that the acceleration is the slope of the velocity time graph. And this is a convenient thing, because if I were to collect some data of a more complicated situation where the velocity rises and falls throughout time, I can inspect that graph, and by imagining the slope of the graph, and the slope is very steep, that is a large acceleration. If the slope is very shallow, that is a very low acceleration. If the slope is negative, it's a negative acceleration. So I can interpret the velocity time graph by looking at the slope. It's a very convenient thing, and a skill that is really useful to us in our physics, and will definitely be a skill that will apply when we take our exam. I recognize that the slope of this graph is the acceleration, and it turns out that in this particular situation, because I drew the velocity as a function of time as a straight line, I'm implying here that the acceleration is a constant. I'm implying that the acceleration is a constant, because if the slope of the graph is a constant, then the acceleration itself must be a constant. So this graph applies specifically to a situation where the acceleration is constant. I'm going to come back to this graph again in a minute, but I also want to do exactly the same trick. And pardon me, I'm going to do it quickly because it's, again, making the same argument. I notice there's a pattern here to the arguments that I make, making the same argument again, but doing it with a graph of position as a function of time, where perhaps I start with some initial position x naught, and perhaps the position changes as a function of time like this. Again, a straight line, just in order to make the argument. Well, I realize what happens. I start at some time t is equal to 0, and I go to some time t, where on my graph I find that there's a final position x, which means the amount that the time changes along the time axis here is delta t, and in that time delta t, the position changes by an amount that goes along the vertical axis here, which is delta x. Well, by the same argument, you see here that delta x divided by delta t, it's very much the same argument, delta x divided by delta t, is again the slope of this graph. And the slope of this graph is delta x over delta t, which is what I've defined as the average velocity. And so the slope is the average velocity. So if I have a graph of position as a function of time, and I observe the slope of that graph as a more complicated graph, and I observe the slope, if the slope is very steep, then that is a large average velocity. If the slope is very shallow, that is a low average velocity. If the slope is negative, that is a negative average velocity. So again, by looking at motion graphs, I can divine some information about it. This slope is constant, which means the average velocity is constant for this graph. So from this graph of position as a function of time, if I chose to draw the velocity as a function of time graph, I would find that velocity as a function of time graph to be quite boring. Because if the slope of the position time graph is the average velocity and this slope is constant, It means that whatever that average velocity is, it is that velocity for all time. And I get a graph which is simply a horizontal line. I get a graph that is simply a horizontal line. This is a very simple motion. It's a very simple motion. But it's an interesting one because there's some information that I can divine from it. What happens in it? I'm sorry? That's true. Because the velocity does not change as a function of time, that definitely implies that the acceleration is zero. So there's really no point for me to draw an acceleration as a function of time graph. That'd be ultimately boring. I'd draw the axes and say that. So what happens in an interval delta t? Well, I have a constant velocity for that interval of time delta t. And so what happens, by definition, over here, is that there is a displacement delta x, which is going to be equal to that average velocity multiplied by delta t. You see, all I've done is taken my definition of average velocity and solved it for delta x, so that delta x is equal to v times delta t. Which means that from t is equal to 0 to the final time t over here, which I'll draw in, if I take the average velocity, v, and multiply by delta t, I get the displacement, which means, something rather curious about this, that if I discover the area under this graph, right, if I seek to calculate that, it's a rectangular area. It's very easy to do. I'll take the length and the width of the graph. It's funny because this is a thing you have to transcend in your mind because it's going to come up later. I'm calling this area. Area is length times width, right? So if I really want to find the area of the thing, like if I want to find the area of this tabletop, I'll measure the length of the tabletop as a certain number of centimeters, and the width is a certain number of centimeters. I'll multiply and I'll get centimeters squared. That to us is what area means. I'm being a little free and loose with the definition of area here because the units of the width are meters per second, and the units of the length are seconds. And so the area is measured in meters, not meters squared. Right, so it's area in the sense it's in a sort of a mathematical sense. So delta x here is equal to the area under the curve, which is a valuable thing. It makes me want to figure out a way that I can compute any area under a curve, because I've made for myself here a very simple graph for which it is trivial for me to determine the area. When I talk about slope, slope is easy because we can all look at a graph that's curvy this way and sort of imagine, like, so I guess I sort of imagine like a board or a line that sits on the curve, and as you go around it bends this way and that way. You sort of visualize in your head the slope. The slope is easy to visualize. But imagine I have a graph that's like this, and it does a strange thing like this, and I want to know what that area is. Because I know that the area can be physically meaningful, but I don't want to find that area. But it turns out there are mathematical techniques for that we'll discuss before we even get started in our physics. But for now, I'm going to deal with these simple areas. Now let me show you a trick, an interesting result using graphical analysis. I'm going to go back to this graph of velocity as a function of this first graph that I do that is velocity as a function of time. Because what I've discovered is that if I have a graph of velocity as a function of time, the area under that graph is in fact equal to the displacement. Which means if I take a more sophisticated graph like this one, where I start with some initial velocity v0, and I increase to some final velocity v, if I could determine the area under this graph, and I don't want to hash that area in, but if I could, actually, you know what, I'm going to redraw the graph over here so that I can hash the area, because I have the luxury of doing that. So I'm going to redraw this graph velocity as a function of time, starting with the initial velocity v0 and going linearly up like that. Right, so it's implying that's the same graph there. If I could, with respect to the final velocity here, if I could hash this out and determine this area under the curve, then I verified for myself in the more simple case that that area would in fact be equal to the displacement. So I'll set about trying to compute that. That the area delta, which will be equal to the displacement, so the area, which is equal to delta, I'm going to go ahead and write that as a piece of text here, area equals delta x is equal to. Now computing the area is going to take a little bit more trickery on my part because it's the area of the, what do you even call this? It's not a triangle, is it? It's a triangle with a bit of rectangle on the bottom of it. So I'll simply add those two areas. And I'll start by computing this lower area here, which is simply a rectangular area, which conceptually says, imagine what would the displacement be if I simply went on with the velocity v0. I didn't let the velocity change. I just go along with that velocity v0. What would that displacement be? Well, obviously, it would be v0 times t. It would be v0 times t. So v0 multiplied by delta t. But I would do delta t here. So it'd be v0 times delta t. But delta t is t minus t0, which is t. That's the rectangular area. I have to add to that the area of the triangular region, which is a little bit trickier to get because that area is going to be the area of a triangle, but I know that the area of a triangle is 1/2 the base of the triangle times the height. So here it will be 1/2 the time, because the base is the time, so 1/2 the time, multiplied by the height. And that height is delta V. So now, in principle, I've discovered the displacement of the thing, and I know that out there in the audience there's some suspicion going on, like I see what has developed here. But it's not exactly what I expect. Let me go over here to my definition of acceleration. You see here that I defined acceleration as delta V divided by delta T, and that implies, most certainly, that delta V, which appears, is equal to A times delta T. Now, in the case that I have, delta T is just T, because I've set the initial time equal to 0. And so my delta V that appears here can be replaced by A times T, in which case I write the displacement delta X as being equal to the initial velocity times T plus 1/2 the acceleration multiplied by the time squared. And since delta X is the final position minus the initial position, I can write that X is equal to X naught plus V naught times T plus 1/2 A T squared, which I'm very excited to see, because I know that that is a fundamental equation, like basic physics of kinematics, to predict the position as a function of time. I really don't like the way that I drew that, so as I talk, I'm going to... but I see that kinematic equation appears out of the graphical analysis of motion. Fun thing, is a reiteration of what I said yesterday. You might not have guessed that. Yes, distance is equal to velocity times time. You might guess that. It's pretty obvious and straightforward. But that result is not something, if I went out on the streets and started interviewing people, I expect the people would come up with. And so I check, does it make sense? The initial position has units of meters. This is meters per second times meters, which is meters. This is meters per second squared times second squared, which is meters. Dimensionally consistent result. And you knew that it was, and you know that it's the right result because it's familiar. But again, reiterating, when I come up with unfamiliar results, or if I'm taking our exam and I want to and I'm solving an unfamiliar problem, I get a little nervous. Check the units along the way to verify whether or not something I've done is appropriate. So I've had this so-called kinematic equation that describes the position of the function of time, but I have made an assumption in doing it. This is so critical because for those of you who have already taken a course in physics, this will be the hard thing for you. Those of you who haven't, you'll probably be okay. But if you've already taken a course in physics, this is a really important point. That equation is only true when the graph looks like this. And the important feature of this graph is that the slope of the graph is constant, which means the acceleration is constant. That equation is only true in situations where the acceleration is constant. But a student who takes a more introductory course in physics than this one will go ahead and assume that that equation is true all the time, because an introductory course in physics will not have situations where the acceleration is not a constant. Our exam will sometimes try to trick you by giving you a situation where the acceleration is not constant and tempting you to use a kinematic equation. Only true in situations of motion with constant acceleration, and I am almost immediately going to teach you physics where the acceleration is not constant once we... So I'll leave it to you, just saving myself some time here and some breath. I'll leave it to you to realize that, well, you already realize, of course, that if the slope of this graph is, if the slope of this graph is the velocity, and I rearrange the equation, that in fact v is equal to v naught plus at is another kinematic equation, but is in fact just the definition of acceleration.